The following theorem describes some properties for convergence of a series. First, if C is a non-zero constant, multiplying C to a convergent series yields a convergent series. Similarly, multiplying it to a divergent series yields a divergent series. Second, the sum of two convergent series is convergent, and its sum is equal to the sum of the previous two series. Third, the sum of a convergent series and a divergent series is divergent. And fourth, if two series have exactly the same terms except for a finite number of terms, then convergence or divergence of the first series will be the same with the second series. For this example, let's determine whether the series summation of 2 over n plus 8 with n ranging from 1 to infinity converges or diverges. Note that this series is equal to 2 over 9 plus 2 over 10 plus 2 over 11 and so on, and this can be written as the summation of 2 over n with n ranging from 9 to infinity. Now, this is equal to the summation of 2 times 1 over n with n ranging from 9 to infinity. Now remember, summation of 1 over n with n ranging from 1 to infinity is the harmonic series, and we know that the harmonic series is divergent. Then, the summation of 1 over n with n ranging from 9 to infinity is also divergent. This series, this new series, is obtained by removing the first 8 terms of the harmonic series. Hence, multiplying 2 to this divergent series will also yield a divergent series. Hence, our given series is divergent. For the next example, let's determine whether the series summation of n minus 2 raised to n over the quantity n times 2 raised to n with n ranging from 1 to infinity converges or diverges. First, we will write this complicated looking series as the series of this difference. We have the summation of the quantity 1 over 2 raised to n minus 1 over n. We do this by splitting into two fractions and simplifying each fraction. First, note that the geometric series summation of 1 over 2 raised to n is convergent, and the summation of 1 over n, which is the harmonic series, this is a known divergent series. Now observe that our given series is the difference of these two series, and as such, by the previous theorem, the given series is divergent. Now, this next test can tell us whether a series is divergent. The divergence test tells us that if the series summation of a sub n is convergent, then the limit of a sub n is equal to 0. This is equivalent to saying that if the limit of a sub n as n goes to infinity is not equal to 0, then the series summation of a sub n with n ranging from 1 to infinity is divergent. To prove this test, we will look at the nth partial sums of this series. So suppose S sub n is equal to the summation of a sub k with k ranging from 1 to n. Note that for all n greater than or equal to 2, a sub n can be written as the difference between the nth partial sum and the n minus 1th partial sum. Now, if the series summation of a sub n is convergent, then we know that there is a number s such that the limit of s sub n as n goes to infinity is equal to this real number. Therefore, evaluating the limit of the two sides of this equation, we have the limit of a sub n with n ranging from, or n going to infinity, equal to the limit of the difference s sub n minus s sub n minus 1 as n goes to infinity. And splitting this into two limits, we have the following. Now, using this property, both of these limits will be equal to s. So that gives us s minus s, which is equal to 0. In this example, let's determine whether the series summation of n squared plus n minus 1 over the quantity 3n squared minus 2n is convergent or divergent. In order to solve this problem, we will look at the limit of the terms of this series. In evaluating the limit of the terms of this series, we can multiply both the numerator and denominator by the reciprocal of the largest power of n in the numerator and denominator of this fraction. In doing so, we get the following expression, and note that the fractions in this complex fraction will tend to go to 0 as n goes to infinity, giving us 1/3 as the limit of the terms in this series. And since this limit is not equal to 0, we can conclude by the divergence test that the series is divergent. In this next example, let's determine whether the series summation of n over the quantity 1 plus ln of n converges or diverges. So again, we will look at the limit of the terms of this series, and in evaluating the limit of the terms here, we will be using L'Hopital's rule. So first, consider f of x equal to x over the quantity 1 plus ln of x, where x is in the interval 1 to infinity. We have the limit of f of x equal to the following using L'Hopital's rule. So we have the limit of 1 over the quantity 1 over x, and simplifying this expression gives us the limit of x as x approaches infinity, and this is obviously equal to positive infinity. Therefore, the limit of n over the quantity 1 plus ln of n as n goes to infinity is equal to infinity. Hence, we can conclude by the divergence test that the given series is divergent. However, we must be careful when applying the divergence test. Note that if the limit of a sub n as n approaches infinity is equal to 0, then the divergence test does not give us any conclusion. To illustrate this, let's look at the following series. The first series is a geometric series, summation of 1/2 raised to n, while the second series is the harmonic series, summation of 1 over n, with n ranging from 1 to infinity. Note that the limit of the terms of both of these series are equal to 0 as n goes to infinity. However, the first series is convergent since it is a geometric series with common ratio equal to 1/2, and 1/2 is less than or equal to 1. On the other hand, summation of 1 over n is a divergent series since this is the harmonic series. So remember, the first commandment of series convergence, thou shalt not use a divergence test to show that a series is convergent. To get a better understanding of today's lecture, please answer these exercises. And if you have questions regarding today's lecture, please don't hesitate to contact your Math 22 instructor. Have a good day.